Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a very good morning to everyone. So I will continue lesson for chapter 4, force and acceleration. In this video, we are going to continue our lesson on the second subtopics, planar kinetics equation of motion. Okay. Previously, we already published two videos on explaining mass moment of inertia. So we are going to continue for this video about planar kinetics equation of motion. So in planar kinetics equation of motion, it is divided into three another subtopic. Okay. First is the equation of translational motion. Second, equation of rotational motion. Third, general application of the equation of motion. Actually, to study more detail about this chapter, you can refer to book of Hibbeler. Okay, let's go one by one. For the first one, equation of translational motion. Alright, so the external forces acting on the body represent the effect of gravitational, electrical, magnetic, or contact forces between adjacent bodies. That's why we have sigma here. So in this F, it is represent with gravitational, electrical, magnetics, etc. It is equal to m times ag. Okay, mass times region of the center point G. Okay, we have this one body and the center here is G. Alright, so from this equation, we can divide it into two plane, x and y plane. Okay, sigma fx equal to m agx and sigma fy equal to m agy. Okay, please look at this schematic figure. We have center point G, we have weight, and then we have the mass times acceleration for plane Y from the center point G, and also we have mass time acceleration at X plane from the body center G. Okay, so the translational equation of motion for the mass center of a rigid body. It is actually the sum of all external forces acting on the body is actually equal to the body's mass times accelerating of its mass center. So please remember this equation first. Sigma F equal to MAG. Okay, and it is divided into two plane, X and Y plane. Alright, that's all for equation of translational motion. Second one, equation of rotational motion. Determination of the effects caused by the moments of the external force system computed about an axis perpendicular to the plane of motion, the z-axis, and passing through P. Okay, we have point P here and we have a particle I here. Okay, particle I. The distance between point P to the particle I is R. Okay, alright. So, if the particle has mass m and acceleration a, then its kinetic diagram is this one. Okay, this is the particle kinetic diagram. MIAI. Actually, MIAI is from these two force. We have large F and small f. These two forces represent this value m times a. Okay, what is large F? Large F is resultant external force acting on the particle. Meanwhile, for the small f is the resultant of the internal force caused by its interactions with adjacent particles. Thus, its moment about point P is R times large F plus with R times with small f. And I already told you before, MA is actually equal to these two forces. F and F, small f and large f. That's why we can simplify this equation to R equal to M times A. Okay, so moment at point P for particle I is equal to R times M I A I, particle I. Okay, so this is another equation that you need to remember for equation of rotational motion. The moment about point P can also be expressed in terms of acceleration of point P. Okay, just now, okay, we already determined this equation. Moment equal to R times ma. Okay, so now they want to express this a, this acceleration, okay, since it is in rotational motion, so we just substitute the relative motion analysis acceleration equation inside this equation, okay, then you will get this equation, okay, MIR, just now MI times with R times with A, acceleration, okay, and we consider the angular acceleration as well in this equation. Alright, so letting m to the m and integrating to the entire mass of the body, we will obtain this equation. Okay, actually this equation is written in Hibbeler equation 17.6. The total moment of point P is equal to the y bar. Y bar is the position y and x bar is position x, plus with IP alpha. IP is the mass moment of inertia times with acceleration. Okay, so this is the equation for rotational motion. Alright, if point P coincides with the mass center G of the body, the moments about point P is simplified to moment G equal to IG alpha. Okay, if point P coincides with, if this point coincides with point G, if point G is here, then the equation is simplified to sigma mg equal to IG alpha. Alright. The rotational equation of motion states that the sum of the moments of all external forces about the body's mass center G is actually equal to the product of the moment of inertia of the body about an axis passing through G and the body's angular acceleration. Okay, this yellow box actually explaining about this equation. Okay, alright. So equation 17.6 just now, okay, can be rewritten in terms of x and y components of AG and the body's moment of inertia IG. Okay, actually just now we already determined this equation. Okay, and it can simplify to this equation. Okay, the total moment of point P, okay, is actually equal to negative position at y times m agx plus position x m agy plus ig mass moment of inertia times with angular acceleration. Okay, above result indicate that when moments of the external forces shown on the free body diagram are sum about point P equal to the sum of the kinetic moments of the components of MA about P plus the kinetic moment of IG times alpha. Okay, this yellow box is actually explaining about this equation. Alright. Lastly, number 3, the general equation of the equation of motion. I just summarize all equation that you have found before, okay, in this subtopic. Okay, sigma fx equal to m agx, sigma fy equal to m agy, and sigma mg equal to ig alpha. And it also can be rewritten in this equation. Okay, point P and center point G. Okay? This one is actually equal to this one. Alright. So for exercise 32, example 17.5 from Hibbeler, I will just slightly go through this exercise with you together. Okay, in this example 17.5, the car shown in figure has a mass of 2 megagram and a center of mass at G. Determine the acceleration if the rear driving wheels, rear means behind, are always slipping, whereas the front wheels are free to rotate. Neglect the mass of the wheels. The coefficient of kinetic friction between the wheels and the road is mu k equal to 0.25. Alright, from this figure we can see that the distance between point A to the body's mass center G is 1.25 meter, and then the distance from point B to the body's mass center point G is 0.75 meter. Whereas from the below of the tire to the body's mass center is equal to 0.3 meter. Alright, I actually already draw the diagram of the car as you can see here. Okay, this is the front and this is the back. Okay, I'm sorry because I did draw this figure unproportional to the value. Okay, so actually A to G is 1.25, B to G is 0.75, and this is the back and this is the back wheel. Okay, we have point G here. Alright, and we know that has a mass of 2 mg. Okay, so 2 mg equal to 2 times 1000 kilo, we will get 2000 kilo. So normal force here is F times mg, 2000 kilogram times 9.81 meter per second squared. You will get 19620 Newton. Alright, and then we have also FB. Okay, force at FB. It is the static force friction, and it can be calculated using this equation: mu k times width NB, 0.25 already given in the question, times with NB. So this one is equal to Fx. FB equal to Fx. Since the front wheels are free to rotate and its mass is negligible, the frictional forces on the front wheels are zero. Okay, it is not. It is different with FB. Okay, so FA equal to 0. From equation of translational motion, okay, to the right is positive, so sigma Fx is equal to magx. We learned this before, just now. Just substitute the equation. 0.2, the value 0.25 times NB. Why negative? Because this car is directed to the left. So negative because the direction to the left. Negative 0.25 NB equal to negative 2000 kilogram M times with AG. Okay, I denote this equation as equation 1. So for FY plane, okay, to the up is positive, so equal to MAGY. So we have here NA, NB, and also minus NG. Okay, NG here. Alright, so NA plus NB minus NG is 2000 times 9.81 normal force at position at center, body mass center. Then you will get NA equal to 19,620 Newton minus NB. So I denote this equation as equation 2. Alright, the equation of motion at point B is moment times equal to R times MA. Okay, we learned this equation before. Okay, direction to right is positive, thus, so just substitute the value. Okay, negative NA times width 1.25 meter. Okay, MA is equal to NA. Okay, it's a normal force. Equal to negative NB 0.75 meter plus FB times 0.3 meter. Just do the calculation and you will determine NB. This equation 2, just now, this equation can be used to determine the NA. Can be used to determine normal force at point A. And then once we determine normal force at point B and A, then we can calculate the acceleration at the mass center from equation 1. Okay, that's all for this question. Determine the acceleration of the rear driving. So the question asks you about acceleration, then we already proved the acceleration at point G. Okay, that's all. So for the second example, example 17.6, I already give you the reference in WhatsApp. So please refer to the figure, to the picture, and do it by yourself. Okay, I will continue on the on the third topic, equation of motion translation. Okay, just now we learned about the planar kinetics equation of motion. Now we are going to continue on third subtopic, equation of motion translation under force and acceleration chapter. Okay, so equation of motion translation, what you already know about translation motion. Okay, when a rigid body undergoes a translation, all particles of the body have the same acceleration. This one you already know. Not only acceleration, but velocity also the same. Alright. Furthermore, okay, you already learned this in chapter 1. Okay. So furthermore, alpha angular acceleration equal to 0. Okay. Thus, the rotational equation of motion applied at point G is, okay, sigma moment G equal to Ig times alpha. Since alpha for translation motion is 0, then the moment at point G is equal to 0. Okay, this one is equation of motion for translation of the moment at point G. Alright, so now you already know translation divided into two motion. First is rectilinear motion and the second one is the curvilinear motion. Let's go one by one. First, rectilinear translation. Okay, you can see from this figure, okay, there's a rectilinear translation going on for this point G, for this body. Okay, when a body is subjected to rectilinear translation, all particles of the body travel along parallel straight line path. Okay, you already learned this in chapter 1. So sigma fx equal to magx, sigma fy equal to magy. Moment for point G is 0. Okay, because of this. Okay, because of this. Moment for point G is 0. However, it is possible to sum moments about other points on or off the body, such as moments of mag. Okay, we want to determine moments of other point such as this moment, okay, mag. For example, if point A, okay, if point A lies at a perpendicular distance d, okay, lies at perpendicular distance d from the line action of MA, the moment equation is sigma MA equal to MAG times with D. Okay, so if we know the distance between this position point A and point G, the body's mass center, equal to D, then we can determine the moments of point A, of this point. Alright, so this is for rectilinear translation. How about curvilinear translation? When a body is subjected to curvilinear translation, all particles of the body have the same accelerations as they travel along curved path. So, sigma Fn equal to magn. What is n? N is normal. Okay. Sigma Ft tangential equal to mag t tangential. And the moment, total moment of point G is equal to 0 because of this. Because it's translation motion. Either it is rectilinear or curvilinear, the moment at point G is equal to 0. If moments are summed about the arbitrary point B, okay, we have point B here, then moments B consists of two components, magn and mag-t. Okay, actually this one is equal to this one. Okay, however, it is divided into normal and tangential point. So now, H and E is the perpendicular distance or moments arm from B to the line of action of the component. So here we can see H and E for normal and tangential component. Okay, such similar to this one, we have D here, the perpendicular distance of point A through from point G, body's mass center G. Alright, so we will get the moment at point B is equal to E, okay, the tangential component, okay, times with M AGT. Okay, same, M AG, but then tangential component minus with H, we have distance H here, times with M AG and normal component. Okay, it's the same. However, in curvilinear translation, you have to consider two components, normal and tangential. Alright. Now, for exercise, I will show you one example, example 17.7. Exercise 34. The 100 kilogram beam BD shown in figure is supported by two rods having negligible mass. Determine the force developed in each rod if at the instant theta equal to 30 degree and omega equal to 6 radian per second. Okay, for this question, I already include the solution in this video, and I will also attach this solution in the Google Classroom. You can just refer and go through by yourself. Okay, so that's all for this video, for this subtopic. I will continue on chapter 4, which is the most important subtopic in chapter 4 in the next video. Thank you very much, and Assalamualaikum warahmatullahi taala wabarakatuh.